So today we're going to be going over a fundamental topic in calculus, and this is called the concept of limits, right? And calculus kind of builds on this fundamental concept that, helps you understand derivatives and integrals and everything beyond that. So to understand limits, let's first start off with understanding how do we evaluate functions normally. What we get is when we're directly evaluating, you just kind of plug in 2 for x, right? So then we get 2 squared here, which we know is just equal to 4, like that, right? So we know that if we were to look at the graph at this point, the y-axis that corresponds to that point would be 4. So this is direct evaluation. And then so now let's kind of try and understand what does evaluating, how does evaluating limits differ? We still want to evaluate the function of 2, but we're going to evaluate with a limit instead. So what this does is instead we evaluate points around 2, not at 2. Right? We evaluate points at around 2, and you get closer and closer to 2, right? And that basically creates points around the value of f of 2, right? And you get closer and closer to f of 2. Right? Let me just put f of 2 here, like that, right? So to kind of make this make a little bit more sense, I'm going to make a table. And then what we're going to have at the middle of the table is basically the point we're actually trying to evaluate with the limit, which is 2, and the actual, let's say we don't really know what the actual value of f of x is at 2, right? So then, first off, like I said, we're going to try and evaluate points around 2 and kind of see what happens. So let's do that. So if we're going towards values that are, if we're considering values less than 2, the values that are around, close to it would be 1.999, 1.99, and then 1.9, right? And you can imagine the zeros after these, so that's why you're kind of getting farther and farther away. So this is 0.001 away, this was 0.01 away, this is 0.1 away. And then on the other side, when we're considering values greater than 2, so on this side, and then the other one was on this side, we're kind of thinking 2.001, 2.01, and 2.1, like that, right? So now what we're going to do is we're going to kind of see, given these values are around 2 for x, what do those values look like for f of x? We'll start from the top. So if we have 1.9 squared, we get 3.61. And let me try and bring it a little bit closer in there. Okay. And then if we have 1.99 squared, we have 3.9601. If we have 1.999, erase that, 1.999, what we get is, squared. Yeah, then we get 3.996001. And you can see a trend here. We're getting closer and closer to the value 4, right? So then let's see what happens on the other side as well. So let me bring back the calculator real quick. So let's start off from the lowest value, so 2.1. Start at 2.1 squared, we get 4.41. 2.01 squared, we get 4.0401, and then 2.001 squared, we get 4.004001. So now the question would be is, let's say you're not given a calculator, you're only given this graph here, right? And then you're asked, fill in the entry for 2, right? The value you would most likely put here, the one that kind of makes the most sense, would be 4, right? So this is the idea of a limit. You don't evaluate it directly at the actual value, 2. Here, like you would actually put in 2 and then square it and you get 4. Here, you find values around 2, and then you see what is the trend, what is the most likely value to be in this actual slot for 2. So this is the idea of evaluating with limits rather than direct evaluation. So, during direct evaluation, it's written like this, as you see here, f of 2. So the notation for limits is, I'll do it in blue here. So limit, you write the actual limit, it's just short for limit, as x approaches 2, or the value you're trying to evaluate at, and then you write the function f of x, right? And then that's going to be, for us, we saw that it's equal to 4, like that. So it's equal to 4. So, and then also you don't have to write f of x there. You could write the limit, and you can actually write the actual function that f of x is equal to. So here you could put x squared instead is equal to 4. And that's completely fine. But anyway, so this is the notation for writing the limit. And conceptually, you imagine like a table, and you evaluate values around the point you're evaluating, and what's the trend that you see from both sides, or what you would fill that slot with. And this is kind of tedious, right? Making a whole table and doing this. So there's ways to evaluate limits that don't involve using this table that we'll go into in the future. But the main question is, why are we doing this, right? So the reason is sometimes you can't really evaluate the function at a certain point, or it doesn't really tell you anything. So one such example, let me change the colors here real quick. One such example would be, let's say we have f of, give me a second, my color isn't changing. Okay, f of x equals sine of x divided by x, right? And let's say we were trying to evaluate when x is equal to 0. So then what we get is f of x, f of 0 is equal to sine of 0 over 0, like that, right? You're already dividing by 0, so that looks pretty bad. You're thinking that this is going to equal infinity, but if you're familiar with your trig, you know that sine of 0 is also 0. So what you get as an output is just 0 over 0, right? And you can't really tell what is this value really equal to. So this is what happens when we're using direct evaluation, like we usually would with functions. So now let's try our other method where we do the limit. So on this side, let me use the same colors from before. Sine of x over x on this side, but we don't know what this value is, right? So let's kind of find values around 0 here. So we know we have negative 0.001, negative 0.01, and then negative 0.1. I'm going to squeeze it in there real quick. And then we have 0.001 on this side, 0.01 on this side, and then 0.1 on this side, right? So then let's kind of... Oh yeah, sorry, there was a little error with my calculator. So if we start again with from the top of the graph, we have negative 0. Top of the table, we have negative 0.1 divided by negative 0.1. That gives us 0.99833, right? And then if we go on to negative 0.001, which is closer to 1, we get 0.999, and then onward. And then if we add more zeros in, we get closer to more 9s, and then onward, right? So that's that side of the graph. So let's fill that in real quick. So then now let's do the same thing for the other side of the table. So what we have then is we're going to have sine of 0.1 divided by 0.1. We get 0.99833, 4166. And then if we add the add zeros in here, we get 0.9998333. And then if we add more zeros in here, we get 0.999999833, right? And as you can notice, these are the same exact values of the ones up here. So if we ask ourselves what value will we put into here, right, we would say 1, because from both sides we see that it's approaching 1. So this is kind of the utility of limits, right? You see how here when we do direct evaluation we get something that doesn't make sense, but when we apply the limit we get an actual value that we can kind of reason with, right? And so you might be wondering, okay, why does this happen? So if I were to draw out the graph, so it would look like this, right? But at this point here, you have something called a hole, which we'll go into further, where you have the 0 over 0. So here, it's actually not defined, the function. The function is not defined, right? But this doesn't really tell us the kind of the shape of the graph. But the limit kind of tells us where it converges to, because the points around it are defined. So this is a big thing that limits help us do, which lets us do a lot of things in calculus. So we'll be going over a couple more topics involving limits, and then we'll go on to derivatives and how limits are related to derivatives.